let us see what's a conservative force field. So, in a conservative force field, the work done is independent of the path, i.e., it is the same for all the paths connecting the 2 points. That means if I have to move from A to B and I have selected this path and this path, I say this path is 1, 2 and 3, then the work done from A to B by path 1 is equal to work done from A to B by path 2 is equal to work done from A to B by path 3. So these all work done is same. So this is the property of the conservative force field, that is, if you move from A to B by any of the paths, you have to do the same work done. So work done is the line integral of the force along the path traversed by the particle. That means this is written as F dot dl from path 1, that is around A to B. For path 2 from A to B, I say A to B, that is from path 3 from A to B, that is the same. So if this work done or the path integral of F along the curved path traced by the particle is same for 1, 2, 3 paths, then this force field will be conservative, otherwise it is non-conservative. Now let us consider two paths 1 and 2. So now I selected two paths, this A to B from path 1 and from path 2. So I have two paths. So you see, according to the theory, work done from A to B by path 1 is equal to work done to A to B from path 2. So I can write this work done from A to B by path 1. So if I move from A to B, I have to do this work. If I have to come, I have to do minus work. So B to A, path 2. So you see, if I bring this side, that means if I go from A to B by path 1 and then come from B to A by path 2, then the total work done is 0. That means if I go from B to A to B by path 1 and then I am coming by path 2, then that means along the whole path, that is work done from A to B and back to A becomes 0. That means work done along F dot dl along the cyclic path is 0. These are two statements. They are same statements. So work done in this closed path means cyclic path. So thus we see that the statement that the work done is independent of path is nothing but, so thus when the work done is independent of path, then the work done in a closed path is 0. So this is automatically the consequence of this. So the moment I say that work done from A to B, path 1 is equal to work done from B to A by path 2 is equal to work done from A to B by path C, this implies work done from A to B to back to A is 0. So that implies that work done, that is F dot dl along a closed path, this circle means closed path, is 0. So this is the property of a conservative force field, that the work done is independent of the path or work done in a closed path is 0. Now let us study the properties of conservative force field. So properties of conservative force field. So let us see number 1 property. So already given in the definition, the work done is independent of path. So this is the number 1 property. Number 2 property, the work done in a closed path is 0. That is F dot dl along a closed path is 0. Next important property is that they have finite divergence. They have finite divergence, this term. So those students who are preparing for IIT and advanced exam, they have to be careful about these 2 points. Otherwise you can neglect it if you are preparing for some just IP exam, your board exam, CBSE board exam, so you can neglect this 3rd and 4th point. But for IIT, advanced and mains, this is very important. So they have finite divergence. So divergence, this term is introduced. So let us explain this point. The divergence of a vector field V is given by divergence of B. So this term del dot V. Del dot V is read as divergence of V, that is equal to dou by dou x of Vx plus dou Vy by dou y plus dou Vz by dou z, where V is the vector function already specified. So this is what divergence is. This is the mathematical definition. In order to understand the geometry of what we are talking, that is the geometry of force fields, you can see here, let us see here the geometry of these fields. So now suppose I have a field like this which diverges like this. So this field is like this, I have a field like this. So you see, this field is, as you go away, diverging from this point. So this is said to be positive divergence. So I say that del dot V is finite and greater than 0. So del dot V is here diverging, so is positive. is positive, that is greater than 0. If it is inward, this is say diverging field, and I will say converging fields. So again we can have a inward field also like this. So this has a negative divergence, but the divergence is finite. So now I can have a field like this, and I can have a field like this where the fields are parallel. So I say that the divergence is 0. In all these fields, divergence is finite, and so all the three are conservative fields. So conservative fields will have finite divergence. There is one more point. We can have a field which has finite divergence and they may not be conservative force field. For example, if I have a tornado type field like this, if the field vectors are like this and they converge, these are the field vectors. Like this. So these fields have also finite divergence. Their divergence is also finite, So in all the four type of fields, you see the geometry of the fields, you see, and all the fields have finite divergence, but all are not conservative. That means, important point, they have finite divergence. So the divergence of a vector field is like this. So important point here, again one more important point. All conservative force fields has finite divergence. They have finite divergence. But all fields whose divergence is finite are not conservative. So the first three, 1, 2, 3 are conservative, and this is a non-conservative field with a finite divergence. So you can see, whenever the field are radiating or being parallel, you can assume it to be this conservative field. Here also it is there, but there is some rotational character, which we will see that the rotational character of the field makes it a non-conservative force field. So now let us come to the fourth point. Now you see, first point, second point, third point we have discussed. These are the properties. But we can't prove from this that a given mathematical field is a conservative or not. Because in order to prove basically the field is conservative, we have to prove that it is not non-conservative. This is similar to the case in society when I have a passport verification and agency goes for my police verification that whether the concerned person is having a good social character behavior, he is criminal or not. Police never gives us a character certificate that this person is right or wrong or good person. He always tells that there is no case pending against us. Means he proved that he doesn't have a record to prove that this person is a criminal. That means he never gives us a certificate that we are correct people. They just tell that they don't have a record that we have a criminal background. That means we can't prove that the force is conservative, so we should prove that it is not non-conservative. How we can do that? So let us see. The curl of a conservative field is always 0. It is the curl which will decide whether the field is conservative or not. So let us see what is curl. Curl of V is read as curl of V. So curl of V, this is a del, a vector operator. We read is a del, which is a vector operator. So when it acts on V, it gives a quantity which I say curl. This is I, this is determinant form J and K. This is dou by dou x, dou by dou y, dou by dou z. If it is expressed in Cartesian coordinates, Vx, Vy and Vz. So it can be written as I. So you see these two terms are close. So we have this and this, this and this. So we have dou by dou y. This is Vz minus dou by dou z of Vy. This is one term. Now J. So now we have this, that is dou by dou x of Vz minus dou by dou z of Vx plus the third term K. So that is dou by dou x of Vx minus dou by dou y of, dou by dou x of Vy, and this is dou by dou y of Vx. So this whole thing is written in pictorial view in this determinant form as del cross V. Now again, what does del cross V measure? So we say it is read as curl of V. It measures how much the rotational character a vector field will have. That is measured with the help of del cross V. Now let us see the geometry of curl fields. When I say that curl of a field, so you see, first of all, see that if we have a field like this, then this field has a finite curl. So this field has a finite curl. That means del cross V is non-zero. So a rotational, the curl of a vector field, measures its rotational character. So curl of a vector field measures its rotational character. So if we have a rotating field, it will have a finite curl. So this is a finite curl. So if the field is rotational, then it is 100% non-conservative. So if this is non-zero, this becomes non-conservative. If it is zero, it is conservative. So you see here, these were the examples of conservative force field. So here curl of V is equal to 0. It has no rotational character. And here curl of V is 0, no rotational character. Here curl of V is equal to 0, no rotational character. But here curl of V is non-zero, and this is also non-zero. So both curl and divergence here exist. So although it has finite divergence, so since it has finite curl also, so it is a non-conservative force field. So the most important point in determining a conservative force field is that its curl must be 0. So here you see, when the curl is 0, whenever the curl is 0, the force field becomes conservative. So the curl is the parameter which tells the rotational character of a force field. Now let us take a common example to illustrate how a field is rotational and how a rotational field will give a finite curl. So when the field has not to be rotational, then its curl will be 0 and so it will be conservative. So let us talk about the physical meaning, the origin of the curvilinear nature, that is the curling capacity of that function curl. So now you see the physical meaning of curl. Let us calculate the curl of a velocity field. So what we do, this is a, consider a uniform circular motion. This is a uniform circular motion, and at some instant the particle has a velocity, linear velocity v in this direction. This is r and this is theta. So we drop a perpendicular here. This will be y and this is x. So let us calculate now. So physical meaning of curl. So suppose I want to mathematically understand when I calculate curl what actually I am calculating. So let us calculate curl of v, where v is the velocity of a particle which is under uniform circular motion. So now you see v. So this v is tangential, and so it will have its two components. You can see this Vy and Vx. So I can write this V as Vxi plus Vyj, and z component is 0. So Vx, so you see here this angle is theta, this is also theta, 90 minus theta. So we have Vx is equal to this r omega. Omega is the angular velocity. Vx is r omega. Vx is r omega sin theta I plus r omega cos theta j. So V is equal to r omega. Now r sin theta is y. R sin theta is y, omega yi plus omega r cos theta is x, so xj. So this is the velocity vector. Now let us calculate curl of this v. Curl of this is I j k, unit vector I j k, dou by dou x, dou by dou y, dou by dou z, and this is Vx is omega y, this is omega x, and this is 0. So now let us calculate the curl of v. You know this velocity v is linear velocity, and it has a rotational character. So we can't have a better example than the linear velocity of a uniformly moving rotating particle. This has a purely circular character. So whenever a vector field will have a circular character, we will calculate curl of, let us see, calculate the curl of v. It comes out to be I. Now dou by dou I of y is 0, dou by dou z of wx omega x is 0, minus j. Dou by dou x of 0 is 0, dou by dou z of omega y is 0. Then I have k. Dou by dou x of this is omega minus dou by dou y of y is omega, 1 minute, this is actually minus I, omega x is minus I, so we have to put this as I minus y, so here we will have plus here. So now we will get 2k. So what I got, curl of V is equal to 2 omega k. So you can see this x-axis is here and this y-axis is here and z-axis is here. So the direction of omega is half of curl of V. You can see this is k direction is here. So omega is, the angular velocity is a vector in this direction which is half of curl of V and which is a finite quantity. So whenever a vector field has a rotational character, its curl will be a finite quantity. That means whenever I calculate curl, I claim that the field has a rotational character. So if the field has, the geometry of the field is rotational, then it is going to be a non-conservative, and when the field is going to be diverging or converging, then it is going to be a conservative force field. This is the geometry of conservative and non-conservative force fields.